Okay, AP Chemistry students, this is an example problem of how you could look at mechanisms to determine if they are valid. Up on top, we're given a reaction. It's H2, as you can see here, plus I2, making 2HI. And this is the experimental rate law, which was constructed. Notice that there's a negative sign. That negative is because it was based on reactants, meaning that the reactants are being consumed. As I go further in this example, if you negative sign gets dropped out, just realize that's not a big deal. The purpose of that is just mainly that the reactants were being consumed. Okay, so now you're going to look at these three optional, or these three proposed mechanisms to see if they are actually mechanisms for the reaction above. And the first one that we're going to look at is mechanism A. And when you look at mechanism A, you're going to take a look at the slowest step. And that slowest step governs the reaction. So that is what the rate will always be based on, is the slowest step. And if you're going to do that, then you would be looking at this reaction right here, this first step. It's the slowest step. And if we were to write that reaction, we would write the change in I2 concentration over the change in time. And again, you could substitute that for the word rate. That would be fine. Would equal some K constant, which would be my equilibrium constant for step one, and times the I2 concentration. So right here, we can say that no, mechanism A is not a valid mechanism because it does not match this experimental rate law. So for reaction number one, or mechanism A, the answer would be no, that is not a valid mechanism. Looking at this mechanism, it's a one-step mechanism, so it's the only thing we would write the rate law from. So the change in I2, so I'm just picking one of the reactants over the change of time, would equal K times the concentration of H2 times the concentration of I2, and you can see that this would be a yes. This mechanism matches the mechanism, or this rate law matches this rate law. So mechanism B would be a valid proposed mechanism. And then finally, the last one you would want to look at is the slow mechanism for mechanism C, because we're always looking at the slowest step. And here you would say the change in I over the change in time would equal K, and actually we're going to call this K3 because it comes from step 3, times the concentration of H2I times the concentration of I. Now, at first glance, you might think, no, this is not a valid mechanism. And the reason is because this does not match the above rate law here. However, do you notice that H2I and I are intermediates? And that becomes a little bit problematic. You kind of got to think about what that means, is that these two reactions, which are fast, have to happen in order for this reaction to happen, the slower reaction to happen. And in addition to that, this H2I cannot build up in concentration because it's not in my overall reaction. So this H2I, as it's building up, is going to also go into a reverse reaction because it cannot build up, because it's not in the overall equation. Therefore, this is going to happen until you get to an equilibrium state where the rate of H2I is going to equal the rate of consumption here, because it is not, it's an intermediate, so therefore it cannot be in the overall reaction. And that can frankly kind of affect the rate. So what we have to do is that in this mechanism, if you can see this here, it says in the mechanism right here, mechanism C, the rate determining step is step 3 because it's the slowest step. And here I've written the rate law. Both the H2I are intermediates, so they have to be eliminated before the rate law can be compared to the experimental rate law. So in order to eliminate them, this first term right here, I'm going to substitute out this H2I. And what I'm going to do is that looking at the step 2 of the mechanism, so this is the exact same question that, or mechanism that we got, or a step that we got right here, I plus H2 making H2I. So if you're wondering where I got that from, that's exactly the same. We said that it's fast. And just as I had explained, the rate of the forward reaction will be opposite of the rate of the reverse reaction. So I'm showing that with the same value of K, but just that they will be opposite in sign. And so putting these two rates would equal each other because they're done at the same temperature. I can make this term here where K2, the rate law constant times I times H2, will equal the reverse of the rate law constant, H2I. And now solving for H2I, you'll notice that I get H2I is equal to K2 over K2 minus IH2, all right? And then substituting then in this H2I, just like I said I was going to do up here, I'm substituting in this H2I. Now, I am going to substitute in, here's the H2I, so I'm going to substitute in all of this for the H2I. And when I do that, that's what's coming right here. Simplifying this, I have two i's, so this ends up becoming I squared. And again, we're just doing a simple substitution of that H2I. Now, in the mechanism of the rate determining step, and here's the rate law, and here I've substituted in that H2I, so now I've got the I2 and the H2. Now what I need to substitute in is the I2 because that is not part of the mechanism. So we know from step 1 of the mechanism, I2 going to I plus I, that was a fast reaction. Setting those two rates to be equal but opposite. We'll then, solving for this I right here, so just solving for I would get the square root of the rate 1 minus rate 2 over AI2. Then I can substitute in just this I. And you can see that I've done that here for this equation. What that allows me to do then is have this simplified, where it's basically one big rate constant times I2 times H2. And you can see that this is this rate constant, which matches the rate constant, if we look up here, that we had for this problem. So those two actually match. The one for C, that when I've done all the substitutions, and this one here. So they indeed match. Therefore, this is also a valid mechanism because the rate law matches the slowest step. And I hope this helps. And good luck.